Okay, so now getting to the big data side of things and machine learning. First, can we start with, because machine learning can seem abstract, but it's obviously incredibly useful. So how do you like to think about what is machine learning?
So I'm going to give you my answer before the thesis and my answer after the thesis, just to show you the difference, because during my work in the thesis, I matured that understanding quite a lot. But before then, what I literally thought of machine learning is that you use computers, and they're almost endless nowadays, computational power and actual resources inside these computers to perform calculations, etc., to do work that human beings cannot do very well and very fast. If we do it well, it takes us years. If we do it fast, it's low quality. If we do it with many people, it takes money. So you start seeing that without the input of a computer, you're starting to have a lot of limitations with the scale of the activity and the task that you can do. So this is what I thought was machine learning to begin with. Right at the beginning was, okay, use computers to have huge amount of data sets. Just in Amazon, we're talking about trillions of lines of user requests, just figuring out what click you made on the website. So just to give you an idea, but also to use in real world scenarios, like for example, these agricultural studies that I did. So after a thesis, I started understanding that in a little bit more detail. So you have different parts of machine learning. You have to understand that you have the quality of the raw data inputs that are coming in. So you can't just accept blindly that any data set that you're receiving is perfect to go. It's perfect to be trained. So you need to be very sure about what you have collected, if you have collected it. If you have not collected it, you have to set the requirements and the constraints very specifically so that the work that comes to you is high quality. That's something that I didn't really think about in the beginning because, oh, whatever, you just get a data set, you download 15 gigabytes of images, run it, done. The computer gets it. No, the computer will give you garbage results if you give it garbage inputs. So the human, let's say, input is still very important, even though I'm not the one doing all of the maths and all the calculations. The human input is very, very crucial because if I give a bad data, it's going to give a bad result. So that's the first thing. The second thing I would say is the segmentation. So segmenting in machine learning would be to basically understanding from the image that you have, particularly in this case, I'm using the example of the imagery because that's what I did in my thesis. But for imagery, you would segment based on features. So for example, pixel similarities, right? You would try and understand on the spectral and multispectral level, how close is this pixel to this other pixel. For example, behind you right now, I see a screen. You have the black and you have the colors. So the segmentation will be able to tell me, of course, you have different algorithms that do different types of segmentations. So with different quality, different speeds, different costs in terms of not just the money that it takes to get this running, but also cost in terms of the server power that you need to run this, if it's a cloud-based solution, something like this. So it will be able to tell me that you have, the black in the middle behind your screen. Mm-hmm. You have the red kind of like in the blocks, the blue in the tiny squares, and tell me with X amount of confidence, with the coefficients we were saying before, that this is what they expect to be the difference in the imagery. So pixel-wise, they'll be able to tell me that I can segment this in this type, this type, this type, this type, something like this. So they don't tell me what it is. So they don't tell me what black is. They don't tell me what blue is. They don't tell me what red is. That is the next step, which is called classification. So the segmentation step is the step where we just figure out that there is a difference existing in, an imagery set or a data set, something that can be collated together as a set of differences. So if you talk about pixels, you have RGB. If this green level is X% similar to this other green level of pixel next to it, then they are together, and again, and again, and again. And then you make a shape, right? Then you get to a pixel which is different, like the green level suddenly it's completely different. And then you realize this is something else. And you can segment that. You can basically separate into blocks. And the algorithm tells you, okay, human being, I figured out that in this image, we have, 4 blocks of different things. Thank you very much. So the next step is, what are actually these blocks in real life? So what do they represent? And this is where the key machine learning implications come in, because the computer is able to perform very detailed algorithms and very complex algorithms to tell you what these are based on ground truth data that you give them. So in the examples of a color, you would train the algorithm to classify black as black. You would train the algorithm to classify red as red. Like, you teach it that this set of pixels and these similarities in the pixels represent the red. These similarities represent the blue, black, etc. So what it means is that the algorithm now has the human kind of like understanding of when I see in your screen black, my brain instantly goes, that's black. You know, I know it straight away. So the machine needs to be able to do that as well before performing the full classification approach, because without doing that, the classification results will be low quality, because what it's basically doing, it will be mixing up specific segmented blocks into the wrong block, into the wrong combination. So it will tell you that red is actually black. It will tell you that blue is actually red, which is not correct. So the classification algorithms, which is the last step I would say that I did for the part of my thesis, was the most important one, because you had to figure out from different algorithms that you ran. For example, I had the decision trees. I had support vector machines. They used Gaussian kernels and different types of kernels. I had the nearest neighbor kernel as well. So different types of classification algorithms that I would train with existing data about, in my case, it wouldn't be colors, but it would be the reflectance from this particular field, which means I can expect this to be dead. I can expect this to be poor quality. I can expect this to be water stressed. I can expect this to be alive. So I would train it with real data that exists and was collected by the farmers. And the machine would then perform the algorithms and tell me quantifiably, okay, at 92% accuracy, for example, I can tell you that this is the water stress 60% content. This is the 60% water stress content, something like this. And what you do is that you compare the result from the algorithm, you compare with the ground truth that exists, it's actually being collected, and you see what the algorithm is telling you. Is it actually the case? First of all, did it get everything right? That's not guaranteed. So it might make some mistakes. Did it do it in a time that makes sense? Did it take you 60 hours to run? Did it take you 60 seconds to run? Did it take you this amount of RAM, actual computational power to do it? Or was it less or more? So all of these different parameters are very important, because you're not going to give a farmer a computer that can run you in 60 hours, hundreds of terabytes of data. You're not going to do that. You're going to give them something that makes sense for the user. So specific users and specific use cases, institutions, fields, and actually agricultural environments need to have specific solutions that are tailored to what they need to do, but need to be high quality. So the combination of this kind of like raw data quality, segmentation, classification, and then output type is very important to give based on the customer that you have, because you're not going to give them, a huge file that has all of the different tiny bits and pieces saying this one pixel is water stress, this one pixel is good crop yield. You're going to give them, for the farmer, a block, for example. You're going to say this 1 meter block, you should probably worry about. This 1 meter block looks good, etc., etc. Whereas to a scientist and the researcher in university, you need to have a classification result which is much more accurate. You need to give something that is much more complex and much more thorough, because then what they do, they use it to train their own future research, to say, okay, this camera gave me this result with this, multispectral input. Let's try this other camera and compare it. Let's try this other speed. You're flying at different speeds. Let's try this other flight speed and compare. You can basically try different control variables using different technologies and compare the quality of these algorithms moving forward. So this is kind of like, I'm sorry if it took some time, but this is the more complex view that I have on what machine learning really means now, which is harnessing what the computer can do for you by giving it the right set of inputs and using whatever algorithm type and algorithm selection is most apt to the customer and to the user that's going into, to make sure that you have the right resources for that task.
Yeah.